Hi there. Okay, we're going to talk about the intermediate value theorem and the boundedness theorem. So let's just jump right into it. So the intermediate value theorem says that if f of x is a polynomial and a and b are two real numbers where f of a and f of b change sign, there is at least one real zero between a and b. So what does this actually mean? My question is, can you draw a picture of what this is trying to get at? So just two numbers, a and b. I think that if you're trying to understand like some of the technical math jargon, it's really good sometimes to just try to draw a picture of what you think it means. So I think you should pause and try that and then hit play and I'll show you. Okay, so I have a graph. This is talking about a graph. I've got two numbers, a and b. So I'm told that the sign of a and b changes. So let's say this is the value of f of b right here, and let's say that this is the value of f of a. It doesn't matter where you put these points. All that matters is that f of a and f of b are basically on opposite sides of the x-axis, okay? Because what this means then is if I were graphing this, I'm going to have something like this happen, right? And there's lots of different ways that this can happen, but what the intermediate value theorem is trying to say is for these 2 points to be connected, the graph will have to cross the x-axis, so there has to be a zero between them. Now there's many ways that this can actually occur, right? So if I wanted to get rid of this, I mean, this isn't the only way that this could occur. You could have multiple crossings of the x-axis. That's a thing that could totally happen. All the intermediate value theorem is saying is that this will cross the x-axis at least once. Okay, so there are some pretty standard exercises that come up to try to understand this. So use synthetic division to show that this polynomial has a zero between 1 and 2. So if we have to use synthetic division, we're going to basically do it twice. The first time using 1 and the second time using 2. So let's set this up. And so let's see, if I set this up, this is -1, 2, -4, and 5. Okay, so let's see, just make that look nice. Okay, so I'm going to draw my line. This is -1, -1, 1. This becomes 1, -3, -3, and 2. Okay, so we're not done. Hold that thought. We're going to do the synthetic division again with 2, and then we're going to compare the results. Okay, so I set up another synthetic division. -1, -2, 0, 0, -4, -8, -3. Okay, so now we can make a conclusion here. So what do I know is the value of f of 1? From the remainder theorem, the value of f of 1 is this right here. So this equals 2. And what is the value of f of 2? The value of f of 2 is this value right here. So this is going to equal -3. So because there is a sign change, so let me make some space now. So because there is a sign change, there is a sign change in the y value, or you could say the f of x value, whichever one you want to say, from 1 to 2. So since we see that sign change, positive to negative, doesn't matter if it goes negative to positive or positive to negative, you just need the change. So because that happens, there is a 0 between 1 and 2. And so that's it. That's what the intermediate value theorem says. Okay, so I have another one here using synthetic division. I just thought this would be a good one to practice on your own. So pause here, give it a try, and hit play when you're ready. Okay, so now I'm going to set up the synthetic division twice. So this will be 1, -4. Don't forget the 0 placeholder, -1 and 3. And then this will be 1 on the outside, 1, -4, 0, -1 and 3. All right, so let's do this. So I've got 1. This becomes 1/2. This will become -3.5. -3.5 divided by, or times 1/2 is -1.75. If I divide that by 2, this becomes -0.875. So let's see, this becomes negative 1.875. I'm running out of room here. So let's see. If I do that one more time, so I get that this is negative 0.9375. So if I add those together, the result, I'll write it down here, 2.0625. Okay, sorry, everything's a little crammed. Okay, so now I'm going to do the synthetic division again. So let's see, this will be 1, negative 3, negative 3, negative 3, negative 3, negative 4, negative 4, negative 1. And so once again, so now I go from positive to negative. So the sign change shows that there is a 0 in between. So again, that's what you're looking for. If you were in like a test situation or something where you're turning something into your teacher, I would want to write a sentence just being clear that you understand that the sign change and the intermediate value theorem say that there must be a 0 in between. Okay, so now let's talk about the boundedness theorem. So let f of x be a polynomial with real coefficients and degree n greater than or equal to 1, and a positive leading coefficient. Let f of x be divided by x minus c. Okay, so the boundedness theorem, actually, these are like the requirements to use it, so it is a little specific. You need the real coefficients, you need something with at least an x term in it, and a positive leading coefficient, so that's important. So there's two different ways to use the boundedness theorem. The first way says that if c is greater than 0, so remember we're dividing by x minus c, so with synthetic division we're using c in the synthetic division. So if c is a positive number and all numbers in the bottom row of the synthetic division are non-negative, then f of x has no 0 greater than c. Alright, so it sounds very technical, but we'll unpack it in a moment. I just want to show you the other side of this theorem. So if c is less than 0 and the numbers in the bottom row of the synthetic division alternate in sign, then f of x has no 0 less than c. Okay, so the keys here. If you have a positive number that you're using with your synthetic division, and you have all non-negative numbers in the bottom, sorry, let me just erase that. Okay, it's not letting me erase. Then there is no 0 greater than c. That's like the key. Now the flip side of this is if you have a negative c in your synthetic division and you have alternating signs, then there is no 0 less than c. So just pointing out some of the key things. Okay, so let's do a problem just to make sense of this. Okay, so I want to show that this function has no 0 less than negative 3. So what I need to do is I need to set up synthetic division. This will be 1, 0, 5, 3, and negative 7. Okay, so I bring the 1 down. 1 times negative 3 is negative 3. Add those. This becomes negative 3. This becomes positive 9. This becomes 14. This becomes negative 42. So that's going to be negative 39. And then this will be 117. So that's 110. Okay, so notice we had a c less than 0. So that's what the that's what the second part of this said, c less than 0. So if all of the numbers in the bottom row alternate in sign, then there is no 0 less than c. So notice we're alternating positive, negative, positive, negative, positive. So what this means then is that if you were trying to find your zeros, let's say you had like the list of rational zeros and you were like thinking, oh, I'm going to try negative 5 next. If you had this result, then you would know not to try anything less than negative 3. So the way I would explain this is that the bottom row alternates in sign, so there is no 0 less than negative 3 for f of x. So if you pay attention to your synthetic division and you notice things like this, this just kind of helps you make stronger guesses. Okay, so let's do this one more time. So now we want to prove that this polynomial has no 0 greater than 2. So we'll set up the synthetic division again. So let's see, this will be 2, -1, 2, -2, 4, and -4. So this is 2, 4, 3, 6, 8, let's see, 16, 14, 28, 32, 64, and 60. That's what I get. Okay, so now we have a positive C here. So positive C, C greater than 0, and the last row is all non-negative. So there is no 0 greater than C. So notice all of these, they're not negative. So my conclusion then would be there is no 0 that is going to be greater than 2 because the bottom row is all non-negative. So again, like if you're trying to find a 0 using the rational zeros theorem and you notice these types of results, this helps you narrow in on what better guesses are. Okay, and so that is the intermediate value theorem and the boundedness theorem using synthetic division. So I'll just leave it there. So thanks for watching, guys. I'll catch you in the next video.